Hi, this is Lori and welcome to my series on the Pico W. This is part 7 in the Exploring LED Displays series. In this episode, we'll take our 4-digit 7-segment display and control it using our shift register. This is a slide from part 6 where we introduced the 4-digit 7-segment display. So in part 6 we got the basics working pretty well. But we connected every one of our pins over here, all 12 of them, we connected them into our Pico to control them. Now we're going to connect in our segments, A through G and the decimal point, into our shift register, and only the digit control pins will connect in to our Pico, as well as the control pins for the shift register. So that's a choice you have to make. You will see some people use 2 shift registers, one for the digit control pins and one for the segments. That's certainly possible. I just started working with just the segments, and maybe at some point I'll go back and connect in all the digit control pins to another shift register. So that's an extension you could make, and it might be a fun project to do after you watch this video. Here's the circuit we'll use for this episode. Here's our 4-digit 7-segment display, all connected, the segments all connected through current limiting resistors, and then those segments are then connected into our shift register, and then the pins that we have going to our Pico are the D1 through D4 and the shift register control pins. Now I'm going to use a different version of a network resistor to replace these individual resistors. You might remember from the previous episodes in this series, when we were working with the bar graph, we used a network resistor. We used this single inline package version, which had a common pin and then resistors that connect through that. And in this circuit, it is easier to use a dual inline package network resistor, and I managed to get some in from, I got these from DigiKey recently, and this will show up in one of my mail bags at some point. And I think these are pretty nice for this situation, and as I pointed out previously, in this case, maybe the cutaway is the best place to look. You get a resistor across each of the pins as you cross the epoxy covering. There's a resistor in there, so I happen to have one that has 8 resistors. So there's 8 pins on one side, 8 pins on the other. So it's this kind of an array. I have an independent resistor array. And as I mentioned before, it can be a little tricky to work with and think through what's the right one to have for your situation, or which one's the most convenient one to have for your situation. And so you do have to understand they could look the same, but they could actually have different arrangements. So make sure that you, when you order them or pick them up, that you understand which version you have. All right, so let's do some programming with this. We've worked with the shift registers before in the previous episodes. We've worked with the 4-digit 7-segment display. So now we're kind of just putting together pieces and making them all work together. And it can be a little challenging depending on what you're trying to do. So we'll just take a quick look at the real circuit. You can see again I've made my own jumper wires to try to keep this all together. And again, I have wired and rewired this many times to get it solidly connecting everything in. So don't give up hope, keep trying. And you'll eventually get it all connected correctly. And so it does kind of look like a mess of wires, and of course this is why people use driver chips to really do this in real life, because this is a lot of work to control this little display. And under here you see the other little IC. This is the network resistor instead of those individual. Now it takes up the exact, well, I guess it takes up the exact same space. You could jam in 8 individual resistors side by side, but this is much neater and tidier. So I really like having access to some of these. And then here's our shift register, and it's all going, pieces and parts of the controls are all going back to the Pico. But the segments are all connected into the shift register. Only the digit control are connected to Pico and the control of the shift register. All right, so let's go with our first program here. So we'll do some pretty simple things here. We're going to be able to display some digits using the way that we've been using our shift register. You'll see that I have the list of lists to figure out which of our segments we need to turn on to form each of the numbers, and we have our blank line. And we're going to work through the digits as we do our persistence of vision. We're going to work backwards, so this is the ones place and tens and so forth. Then we'll have our functions that we've used many times now to control the shift register. And now our display a digit function will go through and find the correct digit in our list of lists. It will work with them in reversed order, and we did that last time. Just a matter of how I decided to hook up the segments to the shift register. And we'll decide whether to send in a low or a high, depending on whether there's a 0 or 1 for that current bit. We'll tick the clock to get all 8 of the bits in, and then we'll flip the latch to show the number. All right, so let's just do some simple numbers, nothing fancy. So we'll clear the register, we'll turn off all the digits at this point. So we're sending a 1 because we have a common cathode. And now to turn on the ones place, we'll send a 0 for the digit, and we'll go ahead and display the digit 4 on that and sleep, and then turn off the ones place. Then we'll turn on the tens place, we'll display a 3. We'll then move to the hundredths, display a 2, and then the thousandths will display a 1. So let's go ahead and run this. So pretty simple. Now we're displaying each for 5 seconds. Maybe that's a little too long. Goes our 3, our 2, and our 1. All right, so we've got it working, and we can put digits, numbers where in the D1 through D4 digits. We can do that. So now let's go a little bit further. Our second program will be one where we're going to use the persistence of vision so that we can, have numbers on each of the 4 digits simultaneously. And we'll have all our kind of similar setup as we've had before, and our list of lists and all our functions and so forth. And our display digit function, we'll keep that the same. But now we'll need one to display a whole number. So I'll make a function called display a number. And now you'll find out later on I'm going to work on trying to display data with decimal points in it. Let's just start at the beginning and try to walk before we run. So we'll need to say how long the persistence of vision timing should be. And I've had this anywhere from 1,000 to 2,000. I think it can go up almost to 2,500 depending on your setup. But somewhere between 1,000 and 2,000 seems to work, and we'll display default to a second. And you can, we're using the same tricks of how do we get the ones, tens, hundreds, and thousands place for this number that we've input. And we're going to delete any leading zeros that we don't need. And we'll put all those digits together. So we did this in the previous program. And now, we're going to start our clock and display the digit for the correct amount of time, but we'll loop through the 4 places, turning them on and off and showing the correct digit for that place for the persistence of vision time, and then turning it off. And then remember, I added this blanking out to get rid of some carryover. So this program will just do a simple one where we'll display 1, 2, 3, 4 for 5 seconds, but then we'll go through and just do our counter program in this approach. So pretty simple to do the counter program with our display number function all set up. So let's let it go and see what happens. There we go. We've got our 1, 2, 3, 4, and you can see the difference in brightness as we use persistence of vision. And you can kind of see the output just to see what's happening for the digits here. Yeah, so that seems to be working pretty well and allows us to put numbers on and handles them correctly. So our next step is, okay, that's all great, but I think what people would want to do, or at least what I was thinking I'd want to do maybe with the 4-digit 7-segment displays, is be able to display some data from a sensor perhaps. And how do I do that, and how do I make that work? Well, and once we start talking about sensor data, we might also have decimal points to deal with. And right now we've been just working with integers with no decimal points. So a counter is fine for that. But if we wanted to display some data with some decimal points, how could we go about that? So I was thinking of a sensor we could use. There's certainly a whole bunch, and I thought of a temperature, humidity sensor, that sort of thing. But then I thought one of the simplest sensors we could work with would be a photoresistor. And so most people should have one in their beginning electronics kits, and they look like this. They're really inexpensive to purchase if you don't happen to have one. And they're a type of resistor that reacts to the amount of light. They're made of a semiconductor that works that way, and so the resistance is higher in low levels of light and lower in high levels of light. And to hook it up, we'll have to have a 10K ohm resistor to create kind of a voltage divider to allow us to make those measurements. And that was a little confusing to me, but and I'm still not sure I have that one 100% in my mind. But I do have a link here to some discussion about why do you have to have this resistor to measure something with the photoresistor. So if you're interested in that, feel free to take a look at that. I'm hoping as I get a little further along in my understanding of electronics, it'll make a little bit more sense to me. But it's needed, and so we'll add that to our circuit. So let's take a look at our circuit. Yeah, so now our circuit's pretty simple. I just threw in a half breadboard here. I threw the photoresistor on there, and you connect one side to power, and here's our 10K ohm resistor on the other side, and then we have a pin going back to one of our ADC pins so that we can make the measurements and use our ADC converter that we have on our Pico to do that. So our first program with this photoresistor is just to see if we can read the photoresistor and make a very simple program to do that. We'll need to set up the photoresistor on one of the ADC pins. So I'll use ADC 0, which is GPIO pin 26. We'll call it photoresist. And then in our while true loop, we're going to go ahead and read the photoresistor using the read U16 function, which will return a 16-bit value to us between 0 and 65,535. And we'll go ahead and calculate what I'll call a light value. So we'll take that raw value we get from the ADC, we'll divide it by the max, and then multiply by 100. So we should get kind of a percentage light scale. And we'll print that using an F string to our shell, and we'll take a reading every second and keep looping around until we get finished with that. So let's go ahead and run this and see what we get. So yeah, now down here, you can see I'm making sure it's showing in here. You can see the actual value we're getting from the ADC, and you can get the value. So we're shooting for a value between 0 and 100% using the calculation we have here. So that's the kind of range of numbers we have. And you can see where we are now. It's a fairly bright in this room. And if I put my finger over the photoresistor, now you can see the brightness goes down. It's almost impossible. Like if I completely cover it, you can't really get it to go to 0. So it kind of has a limit there. So you can kind of see the range of light, and if I put a bright flashlight over the top, we can get it close to 100%. if you want to do that. So yeah, and hopefully you can kind of see. I'll take a minute here just to do a flyby of the setup because it's hard to get the whole setup into the screen. But there's the photoresistor, connecting back in to the Pico, and then that's all the same part. I have this little blue thing on here to try to make the numbers show up a little better on the filming. All right, so hopefully I didn't mess that up. It's about the best angle I can get with the setup that I have here. Not very pro. All right, so that's we got the photoresistor working. So now instead of having this data here come to the shell, we'd rather it come to our 4-digit 7-segment display. And trying to work with something with a decimal point ended up being an interesting challenge to program, at least with my skills. So it might be possible that I really didn't go about it a very efficient way. But I did manage to get it to work, and I was happy enough with where I got with it. I think there's a lot more you could do to make something very full-featured that would work for kind of any number you put in, but I finally got tired of programming all these exceptions and so forth that I said, okay, it's good enough. It works for the sensor I have. And, again, in real life, we'd probably work with a display that has a driver chip that has a whole bunch of that programmed up for us. All right, so let's take a look at trying to get that done. So finding the decimal point and getting it onto the display turned out to be a little more challenging than I thought. And I had this conception that I was going to make a very thorough set of functions to handle almost any data that you wanted to display. And then I decided that was maybe a little more than I wanted to spend my time on. I made it work with the kind of data we're getting out of the photoresistor, and I think it gives you a hint about how you could do it for maybe other sensors in different ranges if you wanted to. We'll need the math library and a couple functions from that to make this work. We'll set up all our pins for the shift register and for the digits, the control of the digits. And then the first thing that I changed pretty substantially is I moved to a dictionary to to give the code for each of the digits, because now not only do I want to display 0 through 9, but I might want to display a 0 with a decimal point or a 1 with a decimal point. And I needed a way to put that pattern into the list of lists, and that didn't seem very straightforward. So I thought a dictionary would be a better way to do that. So we've got that, we've got just a decimal point, we have a blank, and we have an out of range, which we'll put a dash, so it just turns on the G segment. Because, I didn't want to try to deal with every possible number somebody could type in. Yeah, this is all the same here, setting up the digits and the functions that we've had to run the shift register. And now our display digit goes and looks in the library for the correct pattern of the segments to turn on, and then does the loop for that. So not much happened here. This is pretty similar still. And then I wrote a couple other functions to find where, if there is a decimal point, where is it in the number. And so I found it was easier to work with strings than numbers to try to find decimal points. So I turn things into strings and then search for the decimal point, and this function find here will find a character in a string, tell you where its index is, or it'll give you a -1 if it doesn't find one. So that was pretty useful. So I put that together, find the decimal point, and then I strip out the decimal point as well. You can strip it out using the replace on a string as well. And then I needed something to control the number of significant digits, and I found this function in a discussion about doing that. There was a lot of different approaches people came up with. This was one of the, I won't say the simplest, but the most concise. And so you can see it uses log 10 and floor that it needed from the math, and so it's a little bit of funky math here to figure out how to use round to get the number of significant digits that you want in your number. So now to display a number, our function is going to get a little more complicated, because now we're going to have to work with all those, work with the decimal point, find out where it is, and then pop it back in when we go send it to our 4-digit display. So I'm going to turn the number into a string with 2 decimal places. I decided that's enough to show what we want from the photoresistor. And we're going to figure out if there is a decimal point. We'll keep a hold of that index value. We'll remove the decimal point if we need to. So if that index is greater than or equal to 0, then that means there was a decimal point. And so we can remove it using our function. And this is one of the places where I finally decided to not try to deal with every possible number. I just said if the number is over 1,000 or less than 0.01, then I just want to send out of range and move on. Otherwise, I'm going to try to deal with this number. Okay, so then we're going to figure out how many digits we have, and we'll drop digits after we get the first 4. And then we'll assign them to values digit 1, 2, 3, and 4. And then here we're going to try to figure out where should we add in the decimal place if we need. So this is just the logic to add that in to create the decimal point in the right place with the digit that we want. And then finally, once we're through all that, we should have the count digits correctly identified to send to the display. And we'll start our clock. And then we'll go through and loop through the 4 places, sending the correct pattern to the digit and doing our persistence division and looping back around until we've exceeded the display time. So I have a bunch of tests here that I ran to see if I could get it to work. It will fail under certain circumstances, so it's not perfect code. But I think it works pretty well with the data that we're getting from the sensor and in the range that we're expecting. And you can see even some of these it'll deal with. So let's just see what it does with some of these numbers here. So we'll go ahead and run it. And there's our first one. So it rounded the 0.023, and it does this one correctly. And it did that one right. Yep, that one's right. And now it says this is out of range. And I believe it rounded this one correctly, so that's nice. That's from that significant digit function. And there we go. And now we should get an out of range. It's beyond the range we're going to work with. And this one should also be out of range. So it's fit for purpose, I guess, is the best thing we can say about my function right now. Well, now let's put all that crazy programming together with our reading of the photoresistor and see if we can get the photoresistor readings on our display. Yeah, I'm not going to go through a lot of this code again. We've talked about all of this and all of this, and we have our new functions in here that we needed to deal with the decimal points and our new display number function, which has gotten very complicated. But now, complicated function, but our program's pretty simple. We're going to read the resistor. We'll go and print that to the screen just so we can make some comparisons, and then we'll display it on our display. And otherwise, we'll just turn everything off. So fingers crossed. Hopefully, it works this time. And there we go. So yeah, we're reading in the 80s, and if you flash back and forth, it looks like it's given us the right data on our screen with the decimal point in the correct spot. Now let's do some changing of the values. And it's dropping down. And we'll see how low we can go. We got about to the 30s last time, so yeah. There we go. So that was my foray into trying to get real sensor data on a 4-digit 7-segment display with decimal points, and It's gonna, I think, make me appreciate the library authors who have helped us with the displays that have the driver chips. They obviously put a lot of work into this, or they're way better programmers than me, which is probably true. Well, that's quite a complicated episode. I hope you enjoyed it, and I want to thank you for watching.